All right, section 2.3 covers techniques for computing limits. The first thing we see here is theorem 2.3, and we actually need to remember its name. We have to remember that we're calling it theorem 2.3 because we're going to reference it in just a little bit when we do some proofs. All right, so theorem 2.3 are all of our limit laws, and we have some assumptions up here that say, okay, if we have a function f of x and another function g of x, and their limits as x approaches a exist, then the following properties hold. And then they say some other things like c is a real number, m is greater than 0, and n is greater than 0, and they're both integers. So let's just sort of walk through these. Most of them are very, very intuitive. Let's look at the sum, for example. This is saying the limit of two functions added is equal to the limit of each function then added. So I'll give you a very, very simple example here. Let's say f of x was x and g of x is 2x. Then we could find the limit of x plus 2x as x approaches a. And the way we could do that is we could first add the two functions together. So that would become the limit as x approaches a of 3x. And then we would do a substitution or an evaluation, and we would get 3a as our answer. Alternatively, we could do these individually. We could say, well, the limit of x as x approaches a, and the limit of 2x as x approaches a. Let's see, this should give us, just do an evaluation or a substitution here. So there's no reason why we can't plug a in for x, and then do the same thing here, and we get 3a. So it doesn't matter if you add first and then try to find the limit, or if you find the limit of each and then add, we should get the same answer. And that is true for a difference as well, right? So you could subtract first, then find the limit, or find the limit of each and subtract. Constant times a multiple allows you to take this constant and pop it out front. That might be nice. What if that's a big, huge number, or maybe it's a fraction that makes it kind of clunky to deal with? You could pop the constant out, deal with the limit first, get an answer, and then multiply by c. All right, the next one we have the product rule for limits, right? So the limit of two functions being multiplied is equal to the limit of each being multiplied. Same with the quotient. We always have to remember whenever we're dealing with quotients, though, we have to make sure the denominator is never 0. The power and the fractional power rules are kind of nice because they tell us that it doesn't matter which we do first. We could raise the function to a power and then find the limit, or we could find the limit of the function first and then raise it to a power. It's really whichever one is most convenient for the problem, or gives us the quickest answer. The fractional power or the rational power also just depends on which way is easiest. But remember that this often that fraction often won't reduce, and it will leave us with a rational exponent, which we often will rewrite as a radical. In other words, this will give us roots most of the time. So for example, this might say the limit as x approaches, I'm completely making this up, so that is scary looking for sure. And it could be rewritten as the 8th root of x squared plus 3 to the 5th power, right? That's what the 5/8 tells us we can do. This particular rule says you can figure out what this x squared plus 3 quantity to the 5/8 is first and then find the limit as x approaches 4, or you can actually find the limit as x approaches 4 first and then apply this root. So it's really whichever is easiest for the problem. Note that there are some stipulations on this particular law. It requires that if m is even, in other words, this denominator down here is even, then what that's going to do is it's going to create an even root. Remember, our even roots are the square root, the 4th root, the 6th root, the 8th root, so forth and so on. And remember, if it's an even root, we cannot take the even root of a negative number. So that's why they throw in this stipulation that if it's an even root, that function has to be greater than or equal to 0. All right, if we do end up with an even root, then we have to make sure that the function, again, is greater than or equal to 0. And what we'll often find is that the function, the only way we'll be able to find a limit is a left-handed or a right-handed limit. Graphically, you know, here's what might be going on. You might have a even root that does something like this when you graph it. Okay, well, you can see that we do have a graph to the right of 0, so it would be perfectly fine for us to try to find the limit as x approaches 0 from the right of whatever these things are. But we would not be able to find anything as x approaches 0 from the left, because there's just no graph over there. Okay, so your book goes through sort of painstakingly applying these limit laws and making sure we write every step. We're going to do that once, because I'm telling you, these are going to be intuitively obvious to you, and you're not going to need to spend this kind of time. So we'll do this once, and then we'll move on. So suppose the limit of f of x as x approaches 2 is 4. The limit of g of x as x approaches 2 is 5. The limit of h of x as x approaches 2 is 8. Let's use the limit laws to compute each limit showing all steps. All right, so the fact they say showing all steps is what makes this a little bit longer problem. Okay, so I am definitely going to have equal signs here. And the first thing I'm going to do is sort of split along that addition sign there. So I'm going to break this into 2 bits. We're going to have the limit of 6 times f of x times g of x as x approaches 2 plus the limit of h of x as x approaches 2. Now what some students will do is they'll show too many steps at once, and that ends up unfortunately getting some points off on your exams and quizzes. So truthfully, if they say showing all steps, then you need to show every dinky little step. On this, let's actually put off to the side what law allowed us to do this. All right, so there should be a law up there that says when you're adding, you can do the limits individually. So that is law 1, limit law 1. Okay, the next step then is I see that I have several things being multiplied in this first limit. One of them is a constant, so that constant can come out front, and we now have the limit of f of x times g of x as x approaches 2, and we still have the limit as h of x as x approaches 2 being added. And the law that allowed me to do that was the constant multiple law. So that would be law 3. Right, the next thing I want to do is break up this product. So I'll have the limit of f of x as x approaches 2 times the limit of g of x as x approaches 2, sorry. And then we still have this limit of h of x as x approaches 2 being added. All right, so what I just did there was the product law, which I believe that's law number 4. You do not have to memorize the individual numbers for the laws. It would be nice to know that this is the product law or the constant multiple law. But even then, when we reference this in the future, we're just going to call this theorem 2.3. All right, so the last thing that we can do here is actually do the evaluation. So the 6, right? The 6 will just remain where it is. We can now evaluate or substitute, right, 2 for x. So we have up here that if we are trying to find the limit of f of x as x approaches 2, the answer is 4. And we have from this one that the limit of g of x as x approaches 2 is 5. And the limit of h of x as x approaches 2 is 8. So this gives us 120 plus 8, which is 128. All right. To be absolutely honest, I would hope that you can do much of this in your head. So don't expect a problem as simple as this on the exam. But I do think that most of you could go here, from this step straight to this one. All right, just intuitively understanding that that limit can be, in essence, distributed everywhere. Okay, let f of x equal the piecewise defined function negative 2x plus 4 if x is less than or equal to 1. And the square root of x minus 1 if x is greater than 1. We're asked to find the values of the limit of f of x as x approaches 1 from the left, from the right, and to see if the two-sided limit exists. So what we want to do anytime we have this situation, now we can look at the graph and we know that the two-sided limit does not exist because at x equals 1, the left side of 1, that graph does not meet up with the graph on the right side of 1. So we know that that two-sided limit isn't going to exist, but we need to be able to state it in a mathematical way. So the first thing we'll do is determine the limit of f of x as x approaches 1 from the left. The real reason I put this problem in here is for us to practice which equation we should use inside of that piecewise defined function. All right. So what happens is we have to use a combination of the domain and what we're being asked to look at, right? So we're being asked to find the limit of the function as x approaches 1 from the left. Well, let's think of some numbers that are to the left of 1. That would be things like 0.75, 0, negative 17. All of those numbers are to the left of 1. So think of those numbers that are to the left of 1. If I were to plug them into this piecewise defined function, you don't plug into both pieces of the piecewise defined function. In fact, you would only select one equation for which to evaluate those numbers. So for example, negative 32, that is to the left of 1. Which one of these equations should I use if I'm trying to evaluate x at negative 32? or evaluate f of x at x equals negative 32. Sorry. Well, negative 32 is to the left of 1, so my domain tells me I should be using this top equation. So that gives me an idea that when I'm attempting to find the limit as x approaches 1 from the left, the piece of the piecewise defined function that I should be using is that top piece. So I'm actually going to rewrite it and put in the negative 2x plus 4. Okay, so that part I need to see. I need to see that you actually have given this some thought. You have said, okay, I'm starting off with f of x, but I know that I have to choose which piece to use. So I do need to see both of these statements, this one on the this limit of f of x, and then the one where you actually are choosing which piece of the limit to use. And again, you're choosing that based on what x value you are being told to approach, and that x value tells you which equation to use based off of the little if statements in our domain. Now that you have made or done the hard part and actually selected which one of these to use, the next thing you do is just evaluate. So at this point you toss out the fact that it's from the left, because the from the left just tells you which equation to use, and then you take the number and you evaluate. So you plug it in. So the limit of f of x as x approaches 1 from the left is 2. And in fact, if here's when x equals 1 and I put my pen on the graph that's to the left of 1, and I try to force my pen to slide towards that vertical vertical x equals 1 line, when I land on that line, what is the y value? Where I actually hit that line, and it's a y value of 2. So I feel like I've actually answered this correctly. Let's try again from the right. So the limit of f of x as x approaches 1 from the right. So I do need to see that first step where you actually write f of x. And then the next step indicates you have given this some thought and you've decided that of my two equations, the equation I should use if I'm plugging in a number that is to the right of 1 is the equation for x values that are bigger than 1. So I should be using this bottom equation. Once I've decided which equation I should use, I don't have to worry about being from the right or left anymore. I can just evaluate. So I'll take the number 1 and I plug it in. 1 minus 1 is 0. The square root of 0 is 0. And again, I feel like if I put my pen somewhere to the right, I have to put it on the graph somewhere to the right of 1, and I try to get my pen to slide towards 1, right? But I can't pick it up off the graph, right? As it slides towards 1, staying on the graph, what y value do I end up sliding into? It should be a y value of 0. And I think I've done everything correctly then, because sure enough the graph has a y value of 0 there. And so the last thing asks us to find, or last thing we're asked to do, is to find the two-sided limit. Now here's a very important thing that I always struggle trying to convey this, or convey the importance of this to students. Limits must have something behind them, right? You can't just say limit x approaches 1 equals 3. Limit has to have something right here. It has to have an argument, right? It has to have something there. Okay. Well, if we are using a piecewise defined function, oftentimes whenever we're trying to find the two-sided limit, we will have to just use the name of the function rather than selecting a particular piece of the function. Because if I'm approaching 1, because the graph basically splits at one. Half of it is using this line, and the other half is using this well, it looks like a root, right? We know it's a root. It's square root of x minus 1, right? So because they're not using the same equation, then we often, when we write our two-sided limits, most of the time, 99% of the time, we're going to have to write just f of x there. We won't actually decide which function to use because we can't. Half the time you're using one, the other half you're using another. So we just write the limit of f of x as x approaches 1, and then we would go look at our left limit and our right limit and decide that, hey, these things, or this two-sided limit actually doesn't exist because from the left we get an answer of 2, from the right we get an answer of 0, so that means that the two-sided limit does not exist. Notice I erased my equal sign there. Remember the equal sign in mathematics, when we actually say it out loud, in discussions or lectures or whatever, we actually say the word is, right? So have you ever seen or heard anybody say is does? You don't normally put two verbs right next to each other like that. So typically you won't put the equal sign there. You'll just say the limit does not exist. Okay. So let's look at the next piece. So evaluate the following. What we're supposed to do here, again, is sort of distribute that limit everywhere. I think most people would intuitively know what to do. I will show all the steps on this one, and then we're never going to do this multi-step thing again. We're just going to show basically algebra. We're not going to show this multi-step stuff for limits anymore. All right, so we'll do this one super quick. What we know is that this limit can actually be rolled out to each piece. So I'm going to save us a few steps here. And I'm going to remember that the limit can go inside of the root. So we know that much. We know that the limit can be distributed to the 3x. And to the 1. We know that the same can be done to the denominator. And at this point we can start evaluating. So I know we could actually show some more steps here, and the limit could apply to the 2x cubed, and so the 2 could pop out front, you'd have the limit of the x cubed, and so forth, so on. I want to save us a little bit of time, just sort of remind us that a combination of all of these different laws will give us this as an answer: 2 times 2 cubed minus 7 inside of the root. This would give us 6, or 3 times 2, right? Notice on this last piece right here, there's no place for me to evaluate the 2. In other words, there's no x there for me to plug the 2 in. That's okay. That just means the answer is always 1. It's constantly 1. Hey, makes sense. It's a constant, right? So then we'd get 4 times 2, and then same deal down here, that's just constant. All right, so 2 cubed is 8 times 2 is 16 minus 7 plus 6 minus 1 over 8 plus 1, square root of 9. 6 minus 1 is 5. 9. So we end up with 8/9. Again, lots of steps when we could probably go straight from here to at least here, if not doing some of it in our heads. So just be mindful of that. Probably what you've learned from this is go with your gut. It's right. Okay, there's some other techniques So far what we've done is we've evaluated limits by direct substitution. That's where you actually take the number and plug it in for x. Or we might have looked at a graph and said, okay, we can tell from the graph that the left side and the right side don't match, or the limit from the left as x approaches 1 is 2, because we can look at the graph and see it. But as time goes on, right, we can't, first of all, we can't always go grab a calculator. You're not allowed to use calculator on the exams in this course, but we can't always go grab a calculator or computer, mash stuff in. We're not always going to have a graph. Sometimes if we do, we're not going to have the ability to zoom in and actually look at it and be able to evaluate correctly. So we need some other ways to do this, other than graphing and by just direct substitution, right? So what we're trying to do now is build up some algebra skills. All right, so we have two sort of typical cases that we want to investigate, how we would solve or how we would determine, right, these limits with algebraic methods. If you look at the first one, we have, this is what's called a removable discontinuity, right? It's very easy to fix if we could just plug the hole. What's happening there is, even though the two-sided limit exists, it is not equal to what we get when we actually plug the number into the function, right? So the two-sided limit exists here because the left side and the right side match up. But when we actually attempt to plug the number in to the function, right, it gives us a different value. We thought it would give us this spot right here, but it didn't, right? It gave us something else. The other thing that happens is the left and the right side exist, or the left and the right side both exist and end up touching in the same spot, so the two-sided limit exists, but when you attempt to plug the number in, it gives you no answer, right? It's undefined. So those two scenarios, we can actually, if we sort of work through some problems, we'll be able to anticipate which one of those we are seeing based on some algebraic manipulations. And so that's what we want to do next, right? We're going to find these limits algebraically. We're not allowed to graph the function to determine the limit on the exams, okay? So if I ask you to do something algebraically, don't go graph it. You got to do algebra. All right, here are some suggestions. You don't have to do it in this order, but this is sort of a loose way of approaching these problems. The first thing you want to try to do on any problem out there, if you're asked to find the limit, try to do the substitution. See what happens, because sometimes you can just plug the number in and you get a direct substitution and you're good to go. If that doesn't work, so if you end up with an indeterminate form such as 0 divided by 0, right, that's gross, we can't have that. Or eventually we'll end up with some that are like infinity divided by infinity, can't have that either, right? Or we don't want that anyway. So if we end up with something that's a little squirrely, it usually, for these first couple of problems, it usually is the denominator 0 and the numerator 0, and we got to go do something else. If you end up with something squirrely like that, the first thing I would suggest is trying to cancel an existing common factor. So in other words, factor something out and see if it cancels. If that doesn't work, then create a common factor. And that's usually something like multiply by the conjugate, or maybe reduce so that you can get it down to a common factor that is cancelable. All right, so we're just going to pluck away at these. Of all the, this particular section probably has the most missed problems on the first exam. This is algebra, and for whatever reason, students struggle with it. So just know that if you look at these and you're having problems, know that you can email me, you can come by my office, you can go to the Learning Center and get help, you can Google it, you can go to Khan Academy, right? Whatever you need to do, but you need to tackle this head on. Do not let this fester, because if you try to wait till the day before the exam, you're probably going to feel defeated, and I don't want you to feel that way. I want you to jump in and tackle this and beat the snot out of it now, so that when you get to the exam you feel comfortable and you're able to do this. I don't give you anything on the exam that you haven't seen in the notes or on a quiz, so your notes and your quizzes will be the best way to study for these problems on the exam. All right, let's dig in. First thing I want to attempt is to try to evaluate this thing at 2. Now, I usually do this mentally. You would never do it as part of a big chain of equal signs. So let's just do this off to the side as scratch work. Let's get a pen that actually will show here. Okay, so I'm just going to sort of do this as scratch work. If I find out that this will give me an answer, then I'll actually go write it down as the actual answer with some equal signs. But let's just attempt this. All right, if I were to plug a 2 in to the numerator, I would get what, 4, and then 6 times 2 is 12 plus 8, and in the denominator I would get 4 minus 4. So in the numerator, if I worked all the way across, 4 minus 12 is a negative 8, plus 8 is 0, and then look, 0 over 0. This is what we call an indeterminate form. So certainly we don't like dividing by 0. That's always a big scary thing. But because the numerator is also 0, we're undecided as to what this function actually looks like when it's graphing, what it's actually going to do. The fact that the numerator is also 0 kind of tells me maybe something will cancel, and if I can get that cancellation to occur, then whatever pops out afterward will give me some good details about what the graph will look like and how to handle it. All right, so the fact that I get this indeterminate form, this form that's like, yeah, I don't know yet, okay, so I'm undecided, right? That tells me I got to go do something else. So I attempted to do the substitution, and I didn't get anything useful. All right, so I'm now going to see if I can cancel an existing common factor. So the first thing that I will do is factor this beast, right? So this will become, let's see, what is that? X minus 4 times x minus 2. And in the denominator, we would have x minus 2 and x plus 2. Sure enough, if you can factor and you see something that will cancel, that that's really going to be helpful on these problems. Eventually, you might see a pattern in some of these as well. But certainly, right, certainly we see that there is an x minus 2 in the numerator and an x minus 2 in the denominator, so those will cancel. I expect students to rewrite the problem before they attempt to substitute again. All right, so I do need you to rewrite without those cancellations in there. So rewrite it, x minus 4 divided by x plus 2 as x approaches 2. Once you have canceled, then you go back and you try to substitute. You try to do a direct evaluation again. So I am now going to plug the 2 in. Notice that I'm not writing limit here, right? Once you begin to evaluate, you stop writing the limit. So because I'm plugging the 2 in, I stop writing the limit. This would give me negative 2 over 4, which reduces to negative 1/2. All right, so you're actually done with that problem. And I would need to see on a quiz, I would need to see the equal signs. All right, I would need to see the step where it's factored, this step where it's reduced. And at that point, if you want to go straight from here to here, okay, I guess I'll take that. All right. So let's try the next one. This one's a little different because we have this ugly kind of compound fraction where it's a fraction inside of a fraction. Again, we're going to try to do some scratch work off to the side and just see what happens when we try to do a direct substitution. So if I take 0 and plug it in for x, I end up with scary denominator, right? We know we can't divide by 0. In fact, it made me feel funny to even write it down. I don't like it. In the numerator, we get 2/3 minus 2/3. So we end up with 0 divided by 0. Again, this weird indeterminate form, which tells me I can probably factor or cancel or do something. But I know that a direct substitution isn't going to work, so we've got to do something different here. All right, well, nothing will actually factor out of this, so I now have to move to that create a common factor and then cancel. So there are a couple of ways to deal with this, and I'm going to show you both because I have a preferred method and I don't want you to get confused in future videos if I'm using that method. I don't care which of these you use, provided that you do it mathematically correctly, right? You can't, you got to show me some good math. I don't care which one though. All right, so I'll show you, okay, here's the first way. First way is I'm going to find a common denominator for just that numerator. All right, so this is some old school math. And we got to ask ourselves, okay, what is our common denominator going to be here? So remember, your common denominator, it's got to represent, right? It has got to be a representative for both of those fractions. That common denominator's got to have both a 3 plus x and a 3 in it. Now some students will think, wait a minute, if this is 3 plus x, it's already got a 3 in there, so we don't need to have that 3. Oh, no, no, no. If things are being added or subtracted, then from a number or from anything, right, then they are different entities altogether. So our new common denominator will have to have, because remember our common denominator has to represent, right? So our common denominator has to have both a 3 and a 3 plus x in it. And we're going to use that common denominator for both of our new little fractions, right? Now really what we're trying to do is we're trying to take this old fraction, the 2 divided by the quantity 3 plus x, we're trying to take this old fraction right here and write an equivalent fraction whose denominator is 3 times 3 plus x. Well, that's not nearly as hard as it seems, because remember, in the life of a mathematician, you basically get to do two things when you're trying to make things or expressions equivalent. You can either multiply by 1 or you can subtract by 0. Here's a hint. Subtracting 0 doesn't help you a whole lot in many of these, okay? Sometimes it does, but it's usually in a proof, not in this situation. So you can always multiply something by the number 1 and it will retain its value. It'll just look different. It'll be sort of like if you exchange 4 quarters for $1. They look different, but they still are the same amount of money, right? So it's the same kind of thing here. So we've got 2 divided by 3 plus x, and we need to figure out what we need to multiply it by so that its new denominator is 3 times 3 plus x. Well, since it already has a 3 plus x in its denominator, then the only thing that we need to multiply by is a 3. The only thing we need to multiply the denominator by is a 3. The problem is, remember what we are trying to multiply here. You only have 2 things that you can do in math. Multiply by 1 or subtract 0. Remember what we're trying to do here is multiply by 1. So what does my numerator need to be in order for this entire piece to remain the number 1? Hopefully you're saying 3. Okay, so now I would just multiply straight across. So I get 2 times 3 gives me 6. And we could, I suppose, multiply this 3 to each piece and get 9 plus 3x, but that is never going to be helpful, so don't do it, okay? Don't do it. Don't multiply out your denominators when you do these problems. All right, same deal over here. We want to be multiplying by the number 1, but we're going to be real clever about what our number 1 looks like. It could be anything we want. It could be smiley over smiley. It could be fang face over fang face, right? But that isn't what we are doing here, right? We want it to be 3 times 3 plus x in the denominator. So we know that we want, that we need rather, a 3 plus x in our denominator, so that when we multiply these together, we get the denominator that we want, the common denominator that we want. Well, if we do that, then what does our numerator have to be? Well, because this whole green fraction has to be the number 1, that numerator also has to be 3 plus x. So the denominator I would not multiply out, I would leave it as a 3 times a 3 plus x. The numerators, though, it's usually okay to multiply them. I want to point out that this was a minus right here, so I'm going to drag that minus down. And just for grins, I'm going to write this as a 2, and then the 3 plus x, just so you understand what all is going on there. And you know, if you wanted to do that on this first one, you could say 2 times 3 in its numerator. However you want to handle that. Now let's clean it up. So we know that 2 times 3 gives me 6. That denominator we are going to leave alone because it's already factored. And remember, our goal here is to eventually cancel something. So I'm taking a chance, but I think we'll just leave it alone. Here we would have a 6 plus a 2x. Since these are the same denominator, we could write them as a single fraction. And so we would have 6 minus 2x. 6 minus 6 gives me 0. So I end up with a negative 2x over 3 times 3 plus x. That's all like scratch work. All right, so I come back over here, and all I've done is I've made it so that I understand the numerator could be rewritten as a negative 2x over 3 times 3 plus x, all divided by x. Okay, well, if I were to evaluate again, because after every step we go see if we can evaluate, I would do this in my head, but because I'm making a video, I'm going to write it down. All right, if I plug 0 in, I would get, let's see, negative 2 times 0, 3 times 3 all over a 0, so I would have 0/9 all over 0. 0 divided by 9 reduces to 0. And so again, I get this squirrely indeterminate form. So even though I've condensed this a little bit, I haven't done enough to actually make anything fall out. All right, I'm going to erase this because I need some space. I'm still not done with just trying to reduce this and doing some algebra. Remember back in elementary school, we used a different symbol for division, right? We would sometimes use this symbol, right? So I have an equivalent expression here. Remember in elementary school, you would leave the first fraction, change to multiplication, and flip the second fraction. And then when you multiplied straight across, you would end up with a negative 2x divided by 3 times x times 3 plus x. So I can come back over here and say that this reduces to 2x divided by 3 times x times 3 plus x as x approaches 0. I think most of you see what happens now. But again, if I were to try to substitute, do a direct substitution at this point, I would have 0 in the numerator, and I would get 3 times 0 times 3 in the denominator, and I'd still end up with the 0 divided by 0. But I now see that this x and this x cancel each other. Remember that once you've done a cancellation, I'd like to see it rewritten. Then you attempt to do a direct substitution. So whenever you do the direct substitution, you stop writing the word limit. 3 plus 0 is 3. 3 times 3 is 9, so we get negative 2/9. Now, you saw all the work that I had to do, all the scratch work I had to do on that. This is a perfectly legitimate way of doing this problem. I'm a little bit lazy though, and so I have a different way of reducing this. So I'm going to show you how to do this problem one more time. You might like this a little bit better because number one, it's the method I'm going to use from here on out, right? So get familiar with it. And then number two, it should be quicker once you know what you're doing. All right, so here's what I normally do in this situation, is I say, oh, I have some fractions in the numerator, and I can think of this as being a fraction in the denominator as well. And so when I think of this, I have, let's see, one fraction minus another fraction over another fraction, right? And remember, what did I say in mathematics, especially when you're manipulating expressions, you pretty much only have two things you can do. Multiply by the number 1 or subtract 0. Add 0, right? You can either add 0 or multiply by 1. That's about it. All right. So I, again, am going to approach this as if I'm going to multiply by the number 1, but I'm going to be very, very, very clever about the number 1 that I choose. So again, it could be heart divided by heart, but that's not going to help us. What I want is something that will help us reduce these things out. So I am actually going to choose to multiply this by the number 1, and my number 1 is going to be 3 times 3 plus x over 3 times 3 plus x. Now, where did we get the 3 and the 3 plus x from? Well, I looked at my 3 denominators here, 1, 2, 3, and I found a common denominator, right, that would represent all 3 of them. Well, this 1 down here doesn't need any representation, right? Anything multiplied by 1 is just going to return the same thing, so 3 times 3 plus x times a 1 is still going to give us a 3 times 3 plus x. So basically, if the denominator is 1, we get a freebie. We don't have to worry about it. All right, so I've now decided that my number 1 is going to be 3 times 3 plus x. What the heck do I do with that? Well, we may need to think of these as being little individual fractions themselves. That may be helpful. But what I want to do is I want to multiply everything in the problem by this number 1. So I want to take this and multiply it. So multiply the numerators and then multiply, right, these denominators. Got to be careful with what I say and how and what I mean by it. But basically what I want to do is I want to take this 3 times 3 plus x and distribute it to each piece. So what I'll end up with, now I'm going to do some scratch work here, but in the future, I'm really going to do this in my head, all right? So here's what I've got going on. I'm claiming I've got a 2 over 3 plus x, and I want to multiply it by a 3 times 3 plus x over 1. Look at what happens. The 3 plus x's cancel, and I end up with just 2 times 3, which is 6. We can forget about that number 1 down there. All right, then I've got this negative 2/3, and I want to multiply it by 3 times 3 plus x over 1. Check it out. The 3's cancel. And so now I'd have a negative 2 times 3 and a negative 2 times x. That's my new numerator. In the denominator, I have x over 1 times 3 plus x over 1. Nothing cancels. Okay, so what do I end up with? A 3 times an x times a 3 plus x. 1 times 1 is just 1, so I don't need to worry about writing it down. So I now have a new fraction that is equivalent to the old one. What you will often see in my notes, or if I'm doing a solution for you or something like that, by the way, I don't mind doing that. If you email me and say, hey, I don't know how to do this problem, could you help me out, Miss B? I will write it up and send it back, and if I feel like I need to attach a video to it, I'll do that as well. Oftentimes I will actually post it where everybody can see it, not just you. So, you know, be aware that I don't mind doing that kind of stuff. All right, here's what you'll normally see when I do these, is I think to myself, that common denominator will be 3 times 3 plus x, and I will know that that common denominator can be distributed to every single thing in this problem, because what it's actually doing is taking the number 1 and distributing it through our multiplicative laws, right? So I'm just basically doing a whole bunch of that mess in my head. What happens, again, you'll see this a lot in my notes, is the 3 plus x's will cancel, and so the next thing that I'll have written down is two times 3 is 6. And then here the 3's cancel, so I'll have a negative 2 times x plus 3. That's usually how I'll write it. And then nothing will cancel in the denominator, so you'll just end up with this new kind of fancy denominator. Now, some students kind of get crazy here, right? And they're like, oh man, I see a 3 plus x and another 3 plus x. Those cancel. No, if you cannot factor, then you cannot cancel. I'm not able to factor a 3 plus x out of each piece of this, right? I can't factor a 3 plus x out of that 6. I could factor it out of this piece, and I could factor it out of the denominator. But remember, plus and minus signs separate our different terms, and we've got a term here, in other words, that's 6, that doesn't have a 3 plus x in it. So if you cannot factor a 3 plus x out, then there's no way you can cancel a 3 plus x. So if you cannot factor, you cannot cancel. Okay, what can I do? Well, I can distribute. So I now have the limit as x approaches 0 of 6 minus 2x over 3 times x times 3 plus x. These 6's cancel. And we now see the same problem we saw before. The x's cancel. Please write the reduced form. There's a reason for this. Helps us in future problems. But then now when I plug the 0 in, I can go ahead and do that in my head and get the negative 2/9. I don't care which method you use, but this is the method I will be using. Okay. The next one. If I do some scratch work, I get 2 minus 2, well, I get 0 divided by 0 again. So, okay, again with this indeterminate form that just makes me say, I'm not sure. Okay, this one's a little different, all right? So there's nothing we can factor out of it. So we then have to go to trying to create a common factor. All right, well again, you really only have two choices. multiply by 1 or add 0. That's it. Adding 0 or subtracting 0, however you want to think about it, those, they're not going to work here. Again, that typically works for proofs and that kind of thing, but doesn't really work here. Usually what you're stuck with is multiplying by the number 1, but you get to be clever about what your number 1 looks like. Whenever you see a square root and it is inside a binomial, remember binomial means 2 numbers or 2 pieces, okay? So 2 terms. We have 2 terms here. We've got a 2 and we've got an x, the square root of x plus 2. How do I know we only have 2 terms? Plus and minus signs separate your terms. So you have 1 term, 2 terms. In the denominator, 1 term, 2 terms. Whenever you have a square root, in particular, inside of a binomial like this, man, you ought to hear bells clanging and everything else. This is a big fat hint that you are going to multiply by the conjugate. All right, so here's how it would work. Is you say to yourself, I know I can multiply by the number 1. I know I get to choose what my number 1 looks like, so I'm going to be clever. I am going to have my number 1 be the conjugate. So it's going to be a 2 and a square root of x plus 2, but instead of that sign being a minus sign, we're going to write it as a positive. And what we're doing here is we're taking into account that when we multiply these out, we're going to end up with the same terms, only one of them. Okay, when we multiply this out, we're going to have 4 terms. 2 of them will be exactly the same except oppositely signed. So, let's see what happens here. Okay, I'm going to wrap parentheses around this because that's what we're supposed to do. And let's get to multiplying here. So, each term in the first set of parentheses must multiply by each term in the second set of parentheses. So let's see, we would have a positive 2 square root of x plus 2. And let's see, we would have a negative 2 square root of x plus 2. And let's see, a negative times a positive gives me a negative. A square root of x plus 2 times the square root of x plus 2 gives me square root of x plus 2 squared. So again, what I had here was a negative square root of x plus 2, and I multiplied it by a positive square root of x plus 2. A negative times a positive gives me a negative. Square root times a square root gives me square root squared. All right. In the denominator, we're not going to do anything. We know that we could distribute those, but it's not going to help us. All right, so we have to be strategically, we have to avoid things strategically, okay? So in previous problems, I said, okay, you know, we can multiply out the numerator but not the denominator. That was because we knew that our denominators in our previous one where we had the 3 and the 3 plus x, we knew that the 3 and the 3 plus x would somehow be used to cancel. What's happening in the conjugate is we know that we're trying to get rid of that nasty square root. So whichever piece of your fraction contains the conjugates, that's the one that you will distribute. Whichever piece does not contain conjugates of each other, that one you will leave as is. So the numerator had the conjugates of each other, so that's the one we go ahead and distribute. The denominator does not, so it will just remain as is. I promise you, if you multiply it out, it's going to give you a headache and you're going to get discouraged and you'll probably give up. And this problem really isn't that tough after you've done it a couple of times. You should see that this is the positive version of that term. In other words, those two terms cancel each other out. You will also realize that when you apply a square to a square root, you end up with just the argument. So you'll have the limit as x approaches 2. And we'll have 4. And then don't forget this minus sign right here. So it's minus an x plus 2. Let's distribute. In the numerator, 4 minus 2 gives me 2. And I'm not sure how I feel about this, because I really thought something was going to pop out and I would be able to cancel. And it looks like I came kind of close, right? I've got the numerator, which is a 2 minus x, and in the denominator I have an x minus 2, and that kind of makes me feel like maybe I can do something there. In fact, if you notice, this is a positive 2 while this guy is a negative 2, and this is a positive x while that guy is a negative x. In other words, they're the same except all of their signs are the exact opposite. That actually tells me what I can do here. So I'm going to rewrite this one more time because I think it might make it a little more obvious. I'm going to rewrite that numerator so do you see how the signs, it's the exact same numbers except their signs are opposite? That tells us we can factor a negative. In fact, if I were to, in general, that's what we say. If we write these in descending order, which I did with my numerator, I rewrote it so the x came first and then the 2. We usually say that if they're written in descending order and the leading term is negative, factor the negative out. That's usually more preferred. If I factor a negative out of that numerator, it changes all the signs of the numerator. And now we have the piece that can be canceled. All the while, if I had been plugging this 2 in after each step, if I'd been plugging 2 into each of these pieces, right, or each one of these, right, I would have gotten a 0 over 0 every single time, right? In fact, it's not until you're able to cancel that you'll no longer get the 0 divided by 0. Now, this leaves me with a little bit of a quandary. In the denominator, I end up with 2 plus the square root of x plus 2. But in the numerator, all I've got is a negative, right? It canceled out that x minus 2 in the numerator. Remember, there's an invisible 1 right here that you can make visible if you need. Now if I take the 2 and I plug it in, 2 plus 2 is 4, square root of 4 is 2. I get negative 1/4 as my answer. Okay, let's mix it up, throw some trig in. Trig is scary, but it's okay, right? What ends up happening with trig is students really kind of like, oh my goodness, I don't know what to do, I give up, pies scare me, pies divided by 2 or even worse, whatever. Don't, forget about the pi divided by 2. Remember, I'm going to give you, I try to give you as many points as I possibly can, right? So first of all, if the pi over 2 you just freak out on the exam, okay, put down what you do know and then come back to it, because once you relax, it'll probably come to you. For trig, the one thing that I need to get across to students, first of all, that unit circle. You've got to know your unit circle. Got to. Now, happy for us, we really only need quadrant 1, and then we can duplicate to get to the other quadrants if we need to, right? The other thing we need are some basic trig identities. I'm not saying you got to know crazy, multiplying of 2 different angles and what are they. I don't care about any of those. I'm talking like basic Pythagorean identities, sine squared plus cosine squared equals 1, that kind of thing. Most of the time, a rewrite of a trigonometric function will do the job, okay? Our issue with this particular problem is it's got sines and cosines. We don't like that, all right? We either want them all sines or all cosines. Or if we need to, since there's both sines and cosines in the problem, maybe we could rewrite it as tangent or cotangent or something like that. But what we want is to try to get this down to just sines or just cosines. The mixture is what's causing the problem. The first thing I want to do is remember what I just said. Sine squared theta plus cosine squared theta equals 1. And I could solve that thing for cosine squared. So cosine squared theta equals 1 minus sine squared, right? I could subtract sine squared from both sides of the equation and end up with this statement. All right. Really, the first thing I should be doing is my scratch work, which says I got to find cosine of pi over 2 and square that thing. Okay, well, sine of pi over 2, again, you're just going to have to get these memorized. Sine of pi over 2 is 1. Cosine of pi over 2 is actually 0, and then we want to square that. So we end up with 0 squared over 0, 0 squared is 0. Okay, we get this indeterminate form again. All right, so 0 divided by 0, no good, got to go do some work. We also know that cosine squared theta equals 1 minus sine squared theta, so we could rewrite our problem to say 1 minus sine squared of x over 1 minus sine of x, right? Cosine squared of x would be equivalent to 1 minus sine squared of x. Now you may look at that and go, yuck, you made that worse. I actually didn't, because what I've got is a perfect square. Let's do these with letters. Why did I put a plus sign there? All right, this would be like b squared minus d squared, right? That's factorable. It's a difference of two squares. Remember, one's positive, the other's negative. Hey, 1 is a perfect square. Sine squared is a perfect square. That beast factors. So we now have the limit of 1 minus sine of x times 1 plus sine of x over 1 minus sine of x as x approaches pi divided by 2. Well, the 1 minus sine of x is canceled. We're left with the limit of 1 plus sine of x as x approaches pi over 2. Sine of pi over 2 is 1. We end up with 2 as our answer. Okay. So what I tried to do here, and I know it's long, but what I tried to do here is give you one of every kind of squirrely thing you could see. Every time we ended up with that indeterminate form 0 divided by 0, but the way we approached the problem was different in each one of these. Sometimes we won't be able to do any of these, right? We won't be able to cancel an existing common factor or create one. When that happens, we have one more tool in our arsenal, and it's called the Squeeze Theorem. Okay. The Squeeze Theorem is going to feel a little clunky. The best I can tell you is that you need to think of it as a paragraph that has some very regimented sentences in it. Really what you're doing when you attempt to use the squeeze theorem is you're doing a little baby proof. So you're actually doing some, you know, sophomore and junior level mathematics here whenever you do these, but we need it. It's one of the tools we need in our arsenal, so we're going to go ahead and learn how to use the squeeze theorem. All right, so what happens with the squeeze theorem is you can't get anything to cancel. It's just not being really, really nice to you. But what will happen is you will come to the realization that you might be able to set up an inequality and pinch this stuff. So I don't know if the graph on this is visible, or yeah, I think we can see that without actually clicking on it. So the what we're trying to find here is use the squeeze theorem to determine this limit. So it's x squared times sine of 1 divided by x. The black graph is x squared times sine of 1 divided by x. You see how it's squiggly, right? Squiggles everywhere. So squiggly. Yeah, I do such a good job with this. Okay, so anyway, super squiggly there. But it seems to kind of settle down kind of around 0. And it also appears to have a little bit of symmetry to it around 0, right? The left side kind of looks like the right side. Now the symmetry isn't nearly as important because for us, we're not going to graph this, and we're not going to go into whether things are symmetric and that sort of thing. But it's important to notice that that black graph always seems to be below, in this case, well, you don't see that. All right, it always appears to be below, the black graph always appears to be below that red parabola, and it always appears to be above, you know, if I could draw, right, the blue one. So what does that mean for us? Well, I don't know about you, but squiggly sine function that's bouncing all over the place is more intimidating than a parabola or two, right? So if I can prove that that black graph truly is always between that red graph and the blue one, that's the proof I'm trying to do. If I can prove that that black graph is always between the red graph and the blue one, then maybe I can look at the limits of the red graph and the blue graph, make a decision about them, and say, well, because the black is always between them, then it must be true as well. So to give you sort of a real world example, I don't know if this is a good example, but if Billy makes, we'll talk about salaries here, all right? So Billy's salary is less than or equal to Bobby's salary. Can't spell. And Bobby's salary is less than or equal to Sue's salary. Right? So if I just come out and say, hey, I know this to be a truth, because that's just the way life is. Bobby is less than or equal to, or Billy is less than or equal to Bobby is less than or equal to Sue. I don't know, just pretend this is a truth, okay? And then somebody comes back and says, well, Billy makes $86,000 a year. And then someone chimes in, well, Sue makes $86,000 a year. What does that mean Bobby has to make? If we know this is a true statement forever and always, and we also know that Billy makes $86,000 and Sue makes $86,000, what does that mean Bobby has to make? That's basically what we're trying to do, right? We are trying to come up with a proof of that inequality. Then we'll make a statement about the ends, and that will squeeze or sandwich the middle. Okay, so here we go. I will tell you that when I first started doing the squeeze theorem, the thing that got me was like, How do these people just randomly come up with some old random inequality? How do you know that's to be true? All right, well, I mean, that's probably going to be the hardest part for you guys too. And then it dawned on me, man, I was going for like the whole big enchilada platter. And all I really needed to do was go for like, you know, I don't know, the beans or something on the side. All right, what do I know about this? I know that we've got sine. Oh man, anytime you have a trigonometric function, in particular if it's sine or cosine, you might have a squeeze theorem on your hands. Not always, not always. And in fact, don't assume, right? That's you want to do everything else and then come back to this. But if you do have sine or cosine here, there is an opportunity for you to use the squeeze theorem, and you might be okay with it, because the one thing that every one of you eventually would be able to tell me is that when you draw a graph of sine or cosine, the y values are always between what two numbers? So from the get-go, whether you have sine, right, or cosine, from the get-go, you know that for every sine and cosine function out there, you have a built-in inequality. Because you know that sine or cosine are always between -1 and 1. So if your book or if your instructor are nice to you and tell you you've got to use the squeeze theorem, the first thing you want to go for is that trig function and say, okay, that's where I'm going to start my inequality. Now, part of the problem with this is students don't realize they have to build up to it. Remember how I said enchilada plate? You got to start off with the beans, not the whole, you know, enchilada plate, whatever. I probably need to get a better analogy there, but anyway, you got to start off small and then get bigger, okay? If you look at your limit, it actually has several different pieces to it. We've got the limit piece out here, and then inside of it, we've got an x squared, and then next to it, we've got a sine, and inside of it, we've got a 1 over x, right? So it's got several little pieces to it. Well, I don't even need to really even worry about this, you know, sine has to have an argument with it, so we know we're going to always have to have something behind it, so I'm not even going to make it a different color. It's sine of something. Okay. All right, so let's just try to build up to this. So what I want to do is start off with the innermost piece, so maybe that sine of 1 over x. State an inequality. You're always going to start off with your trig piece, okay? You're going to start off with your innermost piece, state an inequality, and then build outwards. So I'm going to start off with that sine. The next thing I'm going to build in is the x squared, and then the next thing I'm going to build in is the limit. Now there's some sentences I need to write in there, but here's how it's going to go. And you really do need to think of this as sort of a nice little paragraph that you're providing to somebody else. You're proving this for them. All right, so I'm going to start off with recall because, you know, that's what I feel like. So I'm going to say recall. No matter what you got behind your sine here, we know that sine is always between -1 and 1. Now, to be absolutely honest, I'm pretty sure it never actually equals -1 or 1 for this particular problem, because we're saying 1 divided by x, and it really just depends if x is a real number or an integer and all sort of kind of crud. I'm not going to go into all that mess. Who really cares, okay? It's definitely between -1 and 1, and I always put less than or equal. I always put an equal in this, right? Less than or equal. Sometimes your book will just do less than, because they're like, well, we've thought about it longer than you have, and we know it can't ever actually equal. Who cares? I'm not saying anything that's untrue, right? It's less than or equal. If it's never actually equal, so what? It's still less than. So not that concerned about it, but just want to point out that there might be a little bit different approach if you're looking at a book or say Khan Academy or something like that. Okay, I usually throw in some extra stuff. I say, hey, remember, this is for all x's, right? So remember from the very first day we had that symbol page. You might want to pull that out. It's not anarchy or the devil, right? Upside down capital A means for all. For all x's that are elements of the real numbers, all right? So we're saying any x out there will work except for 1. It won't work if x is equal to 0 because that x is down in the denominator and you can't ever divide by 0. All right, so this is just sort of our statement of we know this to be true. This is self-evident. You kind of done the hardest part so far. All right, at this point you just sort of build in. So we now want to discuss, okay, are we allowed to do, so that's the end of the first sentence. Now we want to sort of build up, right? So we've got this sign of 1 over x in the middle part, so we're trying to build this g of x up so that it looks like this. Right now all we have is sign of 1 over x in there. We next need to get that x squared in there. So we know that we need to multiply sign of 1 over x times this x squared. But if we multiply this middle piece by x squared, we're going to have to multiply all pieces by x squared, right? All right, well, what we need to do is we need to make some statements about whether or not we're allowed to do that. If we are, then we go do it. So here are my statements. And this is, you're going to have to do a couple of these, right, before you feel comfortable, but what you should start seeing is it's the same sort of paragraph over and over again. All right, so here's what you would say. If x is an element of the reals, all right, so if x is anything, and x is not 0, right, because that's a stipulation from our previous sentence, then what happens when we say x times x? What do we get? So if x is any number except 0, what kind of number do we end up with when we have x squared? It's any number, square it. Hey, this should be a positive value, right? If x is an element of the reals and x is not 0, then when you square x, you should end up with a positive value. And how do we say positive in math? We say greater than 0. All right. If you have a positive number, then when you multiply an inequality by that positive number, it does not change the direction of the inequality. And that's the thing that we have to worry about. Remember, we have inequalities here, and so if we were to multiply by a negative number, it would change the direction of the inequality. In fact, it would make us split it into two different, and it would be terrible, okay? We'd have to do all sorts of stuff. But here, this is a positive number. It's completely legit to multiply by it. So that's what we're going to say. Multiplying by x squared will not change the direction of the inequality. And yes, you do have to write this. I'm not one for writing a whole bunch of extra steps. If I do write a whole bunch of extra steps, I tell you why I'm doing it, and then I usually tell you you don't have to do it after this point. You pretty much have to write everything on these problems. All right, the result is, so we've stated why we are allowed to do what we are about to do, and then we go do it. So we now are going to multiply every piece of our inequality by x squared. That would give us a negative x squared and x squared times sine of 1 over x and a positive x squared. All right, so we've got our sine of 1 over x in the middle portion of our inequality. We now are multiplying it by x squared, so the last piece we need in there is the limit. And so we are going to remind ourselves that we can apply a limit to anything we want. So we are applying the limit to all pieces of this inequality. This double bar arrow is the mathematician's way of saying if, then. So if this first thing occurs, so if this first piece occurs, then we can assume the next step. So we can assume the limit can be applied to everything. If that's true, then we can do a direct substitution for each of these. So when we plug the limit into this left piece, we get 0. We don't know what happens when we try to plug 0 into this middle piece. In fact, that's why we couldn't do a direct substitution from the start of this problem. If I were to plug 0 directly into it, I'd get 1 divided by 0. 1 divided by 0 is not an indeterminate form, and in fact, it's only the argument of sine. We would never look at that as being some sort of indeterminate form, but I'll have students tell me that occasionally, so I just want to point it out. But anyway, the 1 divided by 0, that's catastrophic failure. You can't do that. The whole thing goes nuts. 1 divided by 0, we don't have any idea what's going on there, and then you have to apply sine to it. That's just worse. And then it's being multiplied by 0 squared, and none of that is anything we can deal with right now. So this is why we're doing the squeeze theorem, because we can't get at that actual limit. We can get at the limit of a negative x squared or the limit of a positive x squared, though. And we now have the scenario that we were talking about with Billy, Bobby, and Sue, right? We have 0 on the far left of the inequality and 0 on the far right of the inequality. And the only way that this can be a true statement is if the limit is also 0. Remember, those triangular dots means therefore. And we used, I'm running out of room here, but we would say by the squeeze theorem. And that's a TH with it. M theorem. All right, so you'll have to do a couple of these, but you'll see how the paragraph is about the same for every one of them. And what you'll find on the quiz for this section is a lot of problems where I'm asking you to sort of work backwards. I give you something that a student has done wrong, and I ask you to point out the mistake. Or I give you all the different components of this paragraph, and I ask you to put them in the correct order, that kind of thing. So your quiz is going to seem very thick, and it's going to seem like the problems are really long, and they're really not as bad as they might appear. It's just wordy. Okay, trying to clean this up a little bit and get you to think about when you should use the squeeze theorem. So it's often used when a trig function oscillates. Now that's the big thing. It's when the trig function oscillates. There are other times you can use it, but for now, you want to think of this when when a trig function oscillates. Now, that's not set in stone, so make sure you don't go back and say, Miss Baumgartner said the only time, because that isn't what I said. All right, I said it's often used. There are other times as well, but for now, based on what we know, mostly it happens when a trig function oscillates. So let's see if we can look at these limits and see if this is going to require a squeeze theorem to evaluate. So this first one, I would say no, because if you look, there's a cosine in every single one of those terms, so you could factor a cosine out. So I'm going to say no on this one. And that's a cosine from the numerator, right? Factor a cosine. Factor out a cosine from the numerator and cancel. So no on that one. What about the next one? There's no trig in that. I wouldn't even think about doing it. It doesn't have to be trig, but for what, for our purposes, yeah, most of the time it's going to be trig, right? So I would say no on this one because yikes, no trig. All right, next one. So we obviously know the answer to the bottom one because that's the one we just did. I don't know what I'm drawing there. Okay, he's kind of happy. I don't know what his deal is. He's got a problem. All right. Yes, right? We know that we are going to have to do a squeeze theorem on that one. We just did it. But what about the one before it? Because it kind of looks like it. It's very similar. Very similar. This one would be, we're not quite to dealing with these limits at infinity just yet, but the fact that this is approaching infinity actually saves us on this one. Think of infinity as being a ginormous number. So now I hate doing this, and don't you ever show anybody that I did this, all right? But if I were to plug infinity in, ooh, I hate it because infinity is a symbol. It's not an actual number. Kind of makes me a little sick to my stomach to even think about it. But if you look at this, if I have 1 divided by infinity, think of infinity as being ginormous, right? It's everybody in the entire United States, and you've got 1 stick of gum, right? You got 1 stick of gum, and you want to divide it by everybody in the U.S. How much gum is each person going to get? They're going to get nothing, right? You got 1 stick of juicy fruit, and you're like trying to shave off little bits for everybody. You're not going to get any gum, right? That's useless. This piece shoots off to 0. Well, what is sine of 0? It's 0. So this limit is actually a direct substitution. So the answer to this is no. All right, so that's the kind of stuff you need to think about when you're trying to decide whether or not you should be using a squeeze theorem. All right. Email me if you have any questions.